Hello, I am Xiangyun Li from EPFL Switzerland. In this video, I'm going to present our work about irredundant buffer and splitter insertion and scheduling-based optimization for AQFP circuit. AQFP, or adiabatic quantum flux parametron, is a superconducting electronic technology featuring an ultra-low energy consumption. It has no static energy consumption and very small switching energy dissipation. In this technology, instead of voltage high and low, logic 0 and 1 are represented by the direction of superconducting current. An important characteristic of AQFP is that every logic gate is clocked. One of the main difficulties in the design automation of AQFP circuits is that it imposes two special constraints that are not required by classical CMOS circuits. First, because every gate is clocked, the input signals to a logic gate must arrive at the same time. In other words, if shortening longer paths is not possible, then we need to insert buffers into the shorter paths to delay them. This is called path balancing. Second, the output signal produced by a logic gate needs to be actively branched by splitters if it feeds into multiple fanouts. This is called fanout branching. In AQFP, buffers and splitters are basically the same component, so I will use these terms interchangeably in the rest of this presentation. Although there have been some works to deal with buffer and splitter insertion and optimization for AQFP circuits, they still make up for more than 50% of the total cost. So in this work, I want to look into more details of this problem. The existing approach proposed by Kai et al. Deals with the AQFP-specific constraints after logic synthesis. It first inserts buffers and splitters to fulfill the constraints, and then does some simple optimization, which they called retiming. Suppose this is a part of a logic network after logic synthesis. The circles are logic gates, and later I will draw buffers and splitters as squares. We insert splitters first. Assume that a splitter can split into at most two fanout signals. This gate has three fanouts, so we need to insert two splitters at its output. Deciding on the structure of this splitter tree is another non-trivial problem, but let's assume we construct it like this. Then this gate has two fanouts, so it also needs a splitter at its output. One important thing to note here is that AQFP splitters are also clocked. So inserting splitters introduces one more level in the circuit. This is different from some other technologies and makes this problem for AQFP more complicated. Then we can see that these two paths need balancing. So we insert two buffers for them. Next, we observe that if we split these two signals one level later, then they can share the path balancing buffer. This simple local optimization is called retiming. With the previous example, we can see that the problem of AQFP buffer insertion is not trivial, not to mention finding a global optimal solution. As a consequence, similar to the previous work, I will focus on buffer insertion as a post-synthesis step without considering any logical restructuring. In this work, I would like to provide a different viewpoint of approaching this problem. First of all of the buffers in a circuit can be grouped by which gate their signal comes from. In other words, it is a union of fanout buffer trees of all gates that we want to minimize. And second, if the levels of all logic gates are fixed, then the minimum fanout tree for each gate is easy to find. I will show a linear time algorithm to do this in the next slide. As a result, the problem now becomes finding a good level assignment for all gates to minimize all fanout trees globally, which is still not a trivial problem, as I will explain in the third part of this presentation. Given the levels of a gate and all of its fanout gates, the minimum number of buffers needed in its fanout tree is unique, and I call this way of inserting buffers irredundant. Formal definitions and explanations can be found in the paper. And now I will only introduce the algorithm by an example execution. Given this gate and its fanouts placed at given levels, we start to insert buffers from the highest level. There are 3 fanouts at level 5. Assume again that a buffer can split into at most 2 signals. So we need 2 buffers at level 4. Then, because there are 2 buffers requiring an input signal at level 4, we need 2 divided by 2, which is 1 buffer at level 3. Similarly, we need again 1 buffer at level 2 and another buffer at level 1. This algorithm iterates over each level once and counts how many signals are needed at each level. So it runs in linear time with respect to the fanout size of the gate. Moreover, as it inserts buffer from the highest level, and it always inserts just enough buffers required by 1 level higher, it splits the signal only at the highest possible level and considers the retiming optimization naturally. Finally, as a byproduct, it also verifies whether the given level assignment is feasible by checking whether there is exactly 1 buffer inserted at level 1. Now, as we have concluded that a level assignment determines the number of buffers needed, the problem is now, how do we derive a good level assignment? The 2 well-known scheduling algorithms are as soon as possible and as late as possible. Here is an example of a circuit scheduled with ASAP and ALAP respectively. They have the same total number of buffers. However, if we observe more closely, we can see that in this part of the circuit, ASAP is actually better. And in this part of the circuit, ALAP is better. This is why they end up with even cost. But in fact, if we schedule this part of the circuit with ASAP and schedule the other part of the circuit with ALAP, then we have an optimal solution with only 5 buffers. The problem is, how do we know which part of the circuit should be scheduled with which method? To balance between as soon as possible and as late as possible scheduling, we propose to move groups of gates together, called chunks. Basically, a chunk is a connected group of nodes that are close to each other, which means they are either at consecutive levels or they are separated by only 1 level and the lower gate has multiple fanouts. So we note there must be a level of splitter at its output. Because these gates are so close, we cannot move them one at a time without rescheduling other gates. So we have to move them as a chunk. In this circuit taken from the previous example, we can find these 3 gates as a chunk, these blue gates as a chunk, and these green chunk including buffers because the lowest 2 gates have multiple fanouts. The interfaces of chunks are where there are flexibilities in the circuit. And then to see whether a chunk movement is good, for moving up, we see if there are more outputs coming out from the chunk than inputs going into the chunk. For example, if we try to move this red chunk up, then there will be 1 buffer eliminated at the output, but 2 buffers inserted at the input. So it's not a good move. On the other hand, if we try to move the green chunk up, there will be 3 buffers eliminated at the output and only 2 more buffers added at the input. So it is a good move, and now we derive the optimal solution we have seen in the last slide. Before going into experimental results, in the last part of this talk, I would like to discuss the various assumptions we have to make about the technology. As a very young emerging technology, AQFP is still rapidly evolving in the physical level, and some possibilities are still open and unclear. For example, whether we need to balance the primary inputs and outputs of the combinational circuit depends on the design of the interfacing registers. If the register outputs are always available, then we don't need to balance PIs. For PO balancing, imagine that there are some POs finishing their computation at higher levels and some POs having shorter paths. If we do not align the lower POs with the critical paths, in the later clock cycles, the shorter paths will simply repeat the same computation and produce the same result at output. So in principle, PO balancing may be unnecessary. For the branching assumptions, it depends on the design and the capability of splitters. After a discussion with the YNU lab specialized in the AQFP technology, we concluded that it is difficult to have registers with unlimited output current, but it may be possible to design high-capacity splitters for high fan-out PIs. However, if high-capacity splitters are inserted right at the register outputs to eliminate PI branching, it is likely that they now must be balanced because splitters are clocked. On the other hand, if the output of a gate is referenced multiple times by POs, because the output current of a gate is limited, it will always need to be branched. We did experiments with all different assumptions discussed before to understand their impact on the number of buffers. First, let us explore the impact of PI and PO balancing. The numbers in this table are the total number of buffers in the set of MCNC benchmarks under each combination of assumptions and using each scheduling method. The column OPT stands for the optimized results after chunked movement. Under as soon as possible scheduling, because all PIs are placed at the lowest level, there is no difference in the PI balancing assumption. Comparing the left and the right, we see that PO balancing buffers make up for about 14%. With as late as possible scheduling, similarly, because all POs are placed at the highest level, there's almost no difference made by the PO balancing assumption. Comparing the upper and the lower numbers, we see that PI balancing makes about 30% difference. Now, let's look at each combination of assumptions separately. When both PIs and POs are balanced, our chunked movement achieves 17% reduction. When only PIs need to be balanced, but not POs, not surprisingly, as late as possible makes things worse. Chunked movement again reduces about 17% of the buffers. Inversely, when only POs need to be balanced, as late as possible eliminated already 33% of buffers, and then chunked movement removes another 6%. And finally, when neither POs nor PIs need to be balanced, somehow surprisingly, as late as possible is still much better than as soon as possible. And combining with chunked movement, up to 31% of the buffers can be removed. If we compare the numbers after optimization alone, we can see again the same conclusion that PI balancing matters more than POs. The second set of experiment tests the impact of PI branching and the different values of the splitting capacity. Only the numbers after optimization are reported here for simplicity. Comparing the upper half and the lower half of the table, we can see that PI branching makes about 50% of difference in buffer count, which is a lot. Comparing the different columns, we see that the splitting capacity, which is the maximum number of signals a splitter can split into, also has some impact on the buffer count. In conclusion, in this talk, I introduced the path balancing and fan-out branching constraints the AQFP technology imposes. And I explained with examples why they make AQFP buffer insertion a complicated problem. In this paper, we introduced a linear time algorithm for a redundant buffer insertion, which subsumes the retiming optimization proposed in previous work. Then we learned that the problem of buffer optimization is a scheduling problem. And we saw that sometimes neither as soon as possible nor as late as possible can achieve a good result. This motivates the effectiveness of chunked movement as an optimization technique to escape from local minimum. And last but not least, we discussed about the various technological assumptions and studied their impacts on buffer count. We found that PI balancing matters more than PO and that PI branching has also a huge impact. All of the implementations are available in our logic synthesis library, MaxTurtle, including interfaces to write the buffered network into a special Verilog format and the verification of buffer networks for AQFP constraints. As future work, we are also developing logic optimization algorithms taking AQFP constraints into account. And we plan to integrate these AQFP-aware synthesis methods with the post-synthesis optimization I introduced in this work. Thank you for your attention, and I'm happy to answer any questions.